If you want to send me questions as you're studying, what I'm thinking right now as far as like a final exam review session, I'm thinking Thursday and Monday. And so if you could send me, like those of you planning to take the final, wanting to attend the review sessions, if you could send me times that would work for you, I'm trying to kind of coordinate those and get those figured out as soon as possible so I can give you guys a better heads up. I think that covers all of my announcements. If you think of anything else, let me know. Yeah.
More question. So is the test the same amount of questions?
Yes. The exam will be roughly 1/4 material, not from the test, but material from the content from each chapter or each test segment. And that's 1/4. That should have been 1/5 because I'm good at fractions. And 1/5, the new material, oscillations and waves. So there will definitely be one of the 3 synthesis questions will be from the new material, and then there'll be, one from. Well, there'll be 2 other questions. You can do the math. It won't be able to take one from each test section. But it'll be the same design. So you'll have the knowledge section with questions from the entire range, broken down by just as far as how much percentage from each test period. You understand when I say test period, I mean like chapter 13 through 15 was the last one, 9 through 12, the one before, and so on. So it'd be 1/5 from 13 through 15, 1/5 from 9 through 12, 1/5, 16, and 17, and so on. Then you'll have the application section with one question from each of those, and then synthesis. Do you have a question, Mike? Oh, no. Okay. That answer your question, Ellen? Okay. DJ.
The synthesis is just 3 selected from any of them?
Well, one will be from chapter 16 and 17. And then the other 2 will be from any of those 4, 2 of the 4 test periods will be covered with the other. Okay, and to remind you, you do not have to take the final exam. It's the top 4 out of 5 exams that count toward your final grade. So I'm trying to have the grades as updated as possible. Tomorrow will be the last homework that you have to do. Thursday morning, I will update the homework, so that should be your final homework grades. So, things are coming in. All the labs are graded except for obviously this one and Lydia's, wherever you are. Yours is still not graded. The lab, I think 6.
Okay,
yeah.
As long as I don't
It will be.
The scrapbook is due this Friday also?
And scrapbook is due on Friday, yeah. So obviously that can't be graded until after as well. But as soon as I can get them, I'll update them. The spreadsheets do work. You can copy and paste into the spreadsheet, and it'll tell you exactly what score in the exam will make a difference. So, if it's going to require 99.9, I saw a person that the spreadsheet said this. Right now, at least, it says 99.9% on the final exam to raise the grade from A- to an A. You probably have better things to do with your time than to cram to try to get 100% on the exam. But if it says, 57% will raise you from a C to a C+, that's probably a good bet to take the exam. Yeah.
Is 74 extra credit points accurate, or is that not?
Is what?
74%, like the last time I checked.
Oh, that's a percentage of 3. So 74% would mean that you have 0.74 times 3 is your extra credit. Yeah, if it was adding 74 total, yes, that would be realistic.
And
yeah.
Will be next Tuesday.
Yes, next Tuesday. I looked it up for Clayton. Clayton, what time is it actually? 1 to 3. Okay. Okay. Any other questions before I start? All right. We're going to talk about sound. The lab today is actually a really simple and easy lab. Goes quick. But we haven't talked about it yet, so I have to lecture on the material so you can understand it. So this is the last content lecture you're going to have. I'll review on Wednesday and I'll review on Friday. I'm not going to put another homework assignment, but this is the last material that would be new for the exam. So just a reminder, sound waves, we had 3 requirements. You have to have a source, you have to have a medium for them to travel through, and then an observer, or else we just really don't talk about them. The quantity or the properties we talk about for sound are, number 1, the pitch. Pitch is the frequency. So low frequency is low pitch. It's a low frequency. It's a high frequency. Like, very simple. The frequencies, I am not going to have time to talk about music, which slays me because it's one of the most fun things to do in this class, I think. But just some basic things. You guys know what an octave is? Oh, okay, that was an octave. I missed. But, you know, octaves, oops, can't write in highlighter. An octave means you double the frequency. So if middle C frequency of C, I don't know if it's C1 or not, so I'm just going to put C, is 256 hertz, then what is the frequency of an octave above middle C?
512.
Close. 512 hertz. And now the one that's a little trickier, what is 2 octaves above middle C?
1024.
Oftentimes people forget that you have to double and they say, well, let's add 256 again. But James nailed it. You have to double again. So going up an octave is going to be different frequency changes for the same note. You're doubling each time. And you might wonder, why is it called an octave? Who knows why it's called an octave?
8 notes at the times.
Okay. Okay, 7 notes. What did you say?
I was saying because it's like 8 notes.
Okay, we have 7 and we have 8. Obviously, oct means 8, but James is right. I mean, you're right too.
Yeah.
It depends on how you look at it, because an octave going note is 1 octave above the last one, and so it's the 8th note to reach the next octave. So there's 7 unique notes, and then you repeat. I will continue on the music ideas when we get to this. Yeah.
This is an interesting observation. It relates to this. So I don't know if you heard, car engines, right?
Yeah.
They have particular sounds and cylinders. What I've noticed is that, like, for example, with V6, that spinning at 2,500 RPM, the C note, you double that, an octave higher, 5,000 RPM sounds like that. So it kind of relates to this.
Yeah, it should. It's making sound the same fashion. In fact, one of the things that I'll talk about with beats comes back to that same idea. So we'll come back and talk about it again. So superposition, or you might be more comfortable with the word superimpose. You superimpose things on top of each other. Superimpose and superpose mean exactly the same thing. The M apparently is immaterial. So superposition is superposing 2 waves on top of each other. That is, if 2 waves occupy the same space, the displacements simply add up. So I have 2 waves shown here. One wave that has, you know what I just noticed? That is not the same wavelength on the first half as it is on the second half. That's nice. But I have these 2 waves traveling, and if they overlap the same place on a string, so one's going this direction, one's going this direction, they overlap, then the string's displacement is simply going to be what I get from adding those up. So if you look at the first half of wave 1, it was above equilibrium, and then wave 2 was oscillating about equilibrium, and so the resultant, you see it oscillating about what was wave 1, because it was the longer wavelength. That's the way it appears. And then for the second half, wave 1 was negative, and you see it oscillating about that. So you have just adding up the displacements at every point to get the resultant. If I have two waves that are exactly the same, these two are exactly the same, and they meet, then everywhere I'm going to be doubling the displacement because they're exactly the same. And so this gave me a bigger wave, and we call this constructive. Oh, I have it written at the top. Constructive, that's a V, okay? Interference. Interference means that they are interacting with each other. What would happen if wave 2 was reversed, if it went down and up instead of up and down? So it was exactly opposite of wave 1. What would happen then when I added them up? Okay, they'd add up to 0. So that's destructive interference. I'm not going to rewrite it. You have two waves, but it's adding up to 0. In real life, something like with my beautiful musical instrument here, I pluck it in the middle and I make a wave, just like what James and I did in class yesterday. I pluck it in the middle now. What kind of wave am I making if I pull up and let go? It's a transverse wave because the velocity is going to be like that and the displacement is vertical. So I'm going to make a transverse wave that comes out, reflects, and comes back again. So I'm going to have the waves come through and meet each other on the way back. It's beautiful sound, isn't it? And so that's setting up what we call a standing wave as a result of the waves going back and forth. So this picture here is illustrating how that's done. So you start with, here's two waves, one's traveling left and one's traveling right. And at this moment in time, they're exactly the same. So if they're exactly the same, what kind of interference do you get? Constructive, so it's going to be a big wave. A little bit time later, this moved to here, and this moved to here. So now we have a peak and a valley at the same place. What kind of interference do I get there? Destructive. Now, note that with constructive interference, these places are both positive. You're going to get a really big positive peak. But these places are both negative. You're going to get a really big negative peak. So when I have constructive interference, it's constructive everywhere, but the actual displacement depends on the waves because the waves aren't at peak everywhere at the same time. As the waves continue, you go through another phase of what kind of interference are we going to have here? Constructive, and then another phase of destructive, and so on. And so what you're going to see is a wave that has some places here and here and here and here where it's always 0. We call this a standing wave when we have a wave that appears to stay in place and just go up and down. And the places where it does not move, we call nodes. The places where we have the maximum motion, we call antinodes. So if you have a standing wave, that's when these words apply. If it's not a standing wave, they simply don't apply. With a standing wave, a node is a place where you have no motion. An antinode is a place where you have maximal motion from maximum positive to maximum negative. So if I look at this wave on the string, if I pluck it, are there any places that you can identify have to be nodes or antinodes? I got two strings. Any place where it has to be either maximum displacement or has to be no displacement? Go ahead.
Whenever it's back at its starting spot.
Well, the node and antinode is, it's always there. So it's not that it moves away and comes back, it always stays put if it's a node. If it's an antinode, it's going to do its maximum displacement between positive and negative. Michael?
Is it the edges?
The ends. The ends are fixed locations. That's just, we physically have them fixed so they can't move. So those have to be nodes if I'm going to set up a standing wave because they can't move. So I'm going to have a wave here that has to have a node here and here. There's no place that has to be an antinode, but there are two places that have to be nodes. So if we set up a standing wave, the shortest distance possible between two nodes, well, the wavelength is going, as you can see, there's one wavelength. And so the distance from node to node is 1/2 a wavelength. So my minimum, well, my required situation of having a node on each end means that I can have a standing wave if I have the separation between the two end holders is 1/2 a wavelength. Now remember, we have the relationship that frequency times wavelength is equal to the wave speed. And so in this case, if wavelength, well, 1/2 wavelength is equal to the length of the string, then that means the wavelength is equal to 2 times the length. And so frequency times 2 times the length is equal to the wave speed, or frequency is equal to the wave speed over 2L. And we call that our fundamental frequency, F sub 0. So if I take this thing and I pluck the string, the pitch you hear is the speed of a wave on that string divided by 2 times the length. So how could I change the frequency of this string? Change the length. So if you're playing a guitar, you have your fingerboard and you press down, and where you press down, you're forcing it to be a node there. So you're shortening the string when you press down on the string, the fingerboard. So you're shortening the length. You have frequency is going to be the wave speed divided by 2 times the length. So you shorten the length. That makes the frequency that it will set up a standing wave go higher. So that's why you change the note you play on a guitar by pressing on the strings. You're shortening the length of the string. What's another thing I could do to change the frequency? We've talked about the length. There's only one other variable there. Change the velocity. Now for a wave on a string, I was going to work this out in the calculus-based class today, but that was the part we didn't get to in the lecture. It turns out that the wave on a string is equal to the square root of the tension divided by the mass per unit length. So if I increase the tensioning, I'm going to increase the wave speed. Hence, I take this, and I will just do that. So you got to figure out which, yeah, that's the tighten. Tighten it, the pitch goes up. Pitch goes up because by tightening it, I raise the wave speed. Now, I'm sure there are some people here who play string instruments. How many people play a string instrument, okay? Okay, we got a grand number of people who play string instruments. What's the difference between the strings on your stringed instrument?
Like between each one of them, or like?
They're actually made so they're all the same length. They're different thicknesses. The reason for that is, once again, the wave speed was the square root of tension divided by mass per unit length. So if you can make that string so it has more mass per unit length, that's going to slow down the wave speed. So a string that is made heavier is going to have a lower wave speed and thus play lower notes. You want to have all the strings roughly the same tension. If not, you're going to start bending the neck. So you have different compositions of the strings so you can keep the tensions about the same. Also, you don't want to have a really slack string and then a really taut string because they would actually sound quite a bit different. So that's the fundamental frequency for a stringed instrument. But that's not the only length that it could resonate at. Remember, our rule was we need to have a node at both ends. So I could have a string. Here's one end, here's the other end. And I could set up a standing wave like this. Now let's talk about the names of positions. What do we call the position for the standing wave right here? It's a node. What do we call it right here? Antinode. Now note the antinode, sometimes it's up, sometimes it's down, sometimes it's at 0. That's why the picture has both maximum and minimum, because the string is going up and down a lot there. On the center of the string here, it's going up and down a lot. And you can actually look at it and you can see, yeah, it's moving a lot there. So that's the antinode where you have the maximum motion. What about this place here? We're back to a node again, another antinode, and finally a node at the end. Now in this case, how many wavelengths are fitting on the string? 1. So my wavelength is equal to the length of the string now. So that means frequency times wavelength is equal to speed. Frequency times length equals speed in this case. Therefore, frequency is equal to speed over length. This one here, I'm actually going to put a subscript 2, and we'll see why in just a moment. Yeah?
So wait, why is it 1 again?
It's 1 because the distance for a wave to completely repeat is called the wavelength.
Okay.
So my second frequency that will resonate, this one here I called f sub 0. I could call it also f sub 1. Be the same thing. This one here we call f sub 2 is the second frequency that it can resonate. We call this second frequency either the second harmonic or the first overtone. First overtone because it's the first frequency above the fundamental. Second harmonic because it's the second frequency that it will resonate at. So you have 2 different tones you need there. Overtone and harmonic. Well, those aren't the only 2 it will play. What would the next length be that it would play a note that would resonate? How many wavelengths should I draw for a standing wave? Just okay, fail. Our rule is we're going from node to node. So here's the 0th node. Here's the first node. Here's the second node. Here's the third node. Here's the 4th node. So the first wavelength that it could support was when the length was going from here to here, 1/2 wavelength. The second one was from here to here, 1 wavelength. What's the third one going to be? 0 to 3, and how many wavelengths will that be? That's right, it's going to be 3/2 wavelengths. This here is a 1/2 wavelength, this here was a whole wavelength, 3/2. And so for the same thing then, f sub 3 will be v over parenthesis 3/2 L. Now I'm going to combine these. I have f sub, and I'm going to put 1 now, is equal to that shouldn't be over 3/2. It should be, I need to be more careful. The wavelength, L is equal to 3/2 wavelength, therefore wavelength is equal to 2/3 L. Now we want to look for a pattern. there's a simple pattern which becomes super obvious if I take F2 and multiply it by 2 over 2. What's our simple pattern? F1 is V over 2L, F2 is 2V over 2L, F3 is 3V over 2L. What's the simple pattern? What would F sub 7 be? It'd be 7V over 2L. Or in general, so the frequencies that this string will play are integer multiples of the wave speed divided by 2 times the length of the string. So notice if I go from n equals 1 to n equals 2, I've doubled the frequency. So the first overtone is an octave above the fundamental. But then the next one is 3/2. That's not doubling 2. The fourth one is going to be doubling again, and so on. So the first overtone is, or the second harmonic is 1 octave. The fourth harmonic is 2 octaves. And go up again, it's what, the eighth is 3 octaves? So you can play octaves, but you play more as you go higher. I just have to mention this. Different stringed instruments sound different, right? Nobody gets a violin and a guitar confused. Why do they sound different? Okay, what did you say? Tone. Okay, the things that we use to describe sound. I got hung up and stopped with pitch. I meant to talk about the 2 other things, how loud it is, which is proportional to, well, dependent on, let's say, the amplitude. Bigger amplitude is louder. And we talked about the decibels last class period. And then there is the tone, or the timbre, or the voice. And the tone, timbre, voice has to do with all of the frequencies present. You can tell the difference in my voice and Leslie's voice. Even if Leslie and I were to say the same thing at the same pitch, you would know the difference. And the reason is because I have a different set of frequencies in my voice than she has in hers. The relative strengths of different frequencies is different, and that's how we know the difference. So different instruments have different amounts of the overtones present to give them a different timbre. Timbre spelled T-I-M-B-R-E. So just get that out there. A reminder, what was the boundary condition, the condition for the wave on a string for a stringed instrument? It had to be at the edges, had to be a note, it had to be stationary. So the displacement had to be 0. There was no boundary condition on frequency. The frequency condition came as a result of that boundary condition. There's no boundary condition on speed. The speed is a result of the physical parameters of the string, the tension and the mass per unit length. So we've already gone through this. Come on. Not sure why. I'm going to skip over this. This is doing the equations for standing waves so you can see the mathematical proof of it. I like these pictures because they show you the string in all positions between the maximum and minimum. Remember when I was drawing these, I drew this part and this part. The other lines to remind you that the string is moving between those boundaries. Where you have a node, it's not moving at all. Where you have an antinode, it's doing the biggest motion up and down. That was a repeat question just in case you didn't get it. Here's our equations. We've done that. Now for something completely different. I have my tuning forks here. Now I played around with these with a few people so they know what's going on. People came up and said, "Why is there gum on this?" It's clay, or modeling clay, and it's for a very specific purpose. If I play this, it plays a note. This here has the pieces of metal going like this back and forth, and it's setting up a resonance. Now, if you look at this, What would you say for the boundary condition at the bottom of the tuning fork? How much is it swinging side to side at the bottom? It's not. If it's going to set up a standing wave, what do we call that? If it doesn't move in a standing wave, we call it a node. So we have a node here. What about the tops? The tops are free to move. They're going to be doing antinodes, it turns out. So on this, we have a node here and an antinode here, and it sets up a standing wave that's, what's the shortest distance from a node to an antinode? No, the amplitude is measured displacement this way. A quarter wavelength, right? If you go from node to node, it's a half wavelength, but an antinode comes midway between, so we have a quarter wavelength is equal to the length of this. And then we once again have the speed depends on the material it's made of. Okay, back to the fun. So I did this one, makes noise. Do this one, makes noise. They sound like the same pitch, right? But here's the thing, this has this little clay on it, little modeling clay, Play-Doh probably. And so that Play-Doh is going to make it a little bit heavier. And what do you suppose being a little bit heavier is going to do to the vibrations? It's going to slow it down a little. If you slow it down a little, what is that doing to the frequency? It's going to decrease it a little. So this one's going to have a slightly lower frequency. Now I'm going to bang these two so they're playing at the same time. It's cool magic, right? Now, describe what you hear. Nathan says beats because he's read up on the screen where it says beats or something, or maybe he knew already. We call that beats or beating. It's getting louder and softer, louder and softer. Why is it getting louder and softer? Because the two frequencies are not exactly the same. They're really close to each other, so sometimes they're what we call in phase, where they're both reaching their peaks at the same time. But then because the frequencies are different, a little bit later they're going to be out of phase, where one's at peak when the other is at a minimum. What kind of interference do we have if they're like this? Destructive. What's the motion of a wave if you have destructive interference? Zero. So your sound you hear is nothing. But if they're like this, then what kind of interference do you have? Constructive, and what does that wave look like? It's increased, so that's going to be louder. It turns out that the beat frequency, the frequency for you hear it getting louder and softer, is the absolute value of the difference in the frequencies. So that has a beat frequency of about 1 hertz. And so that means that the frequency difference between these is 1 hertz. This is something that piano tuners use to tune the piano strings. They want this string to be 7 hertz above that string, and so they play them together and they measure the frequency of the beats. And the frequency, I'm making up the 7 by the way. And if the beat frequency is 7 hertz, then they say, it's the right amount. Now, you want to make sure it's the right distance as well. So you tighten the one string and the frequency should be higher. You got to make sure you do that right. But that's how they determine it. Or going back to what Michael had talked about with the engine, hearing the pitch of an engine. One of the things I've been told that pilots will do if you're flying a twin prop, something that's really kind of important is when you let off the brakes, you want to go straight. You don't want to have one prop spinning faster than the other because that will make you curve. So you set the brakes and you throttle up, you throttle one engine up, you throttle the engine up, and you listen. Because they're beating the air, they're each making a sound, and the frequency of that sound is going to be the speed at which your engine's turning. Well, you actually have, if it's 2 blades in the prop, it would be twice that, but you know what I mean. And so you listen to the sound, and when they're very far apart, you're going to hear a hum that's the difference in frequencies. When you get it down to pretty close to within 20 hertz, you'll start to hear it get louder and softer, louder and softer. And then if you can get it to where they stay at constant pitch without that hum, then they're the same frequency. Then if you let off the brakes, you're going to go straight. So it's, it's a very simple application. I'm not a pilot, but I'm told they do this. Of course, yeah. Here's a picture to show how you have constructive interference here, getting you big, destructive interference here, getting you the small. Just because they're slightly different frequencies. This thing also occurs in space. When I was in graduate school, go Cougs, Washington State University, playing the Alamo Bowl. I like to go out to, I think it's called Lower Granite Dam on the Snake River there. It's near Washington State University. We'd go out there. They called it the dunes. We pretended it was a beach because like here in Nebraska, there's no beach around, so people pretend. I'll tell you, I've seen people have picnics on the sand at Holmes Lake. If that's not sad, I don't know what is. But we would go out there, we play volleyball and whatnot on the Quo Beach. But there was a dam, and you could go in the dam, and if you walk around among those turbines are all rotating at the same speed. And so they're all making a hum, like Michael said with the car engines, that should be about 60 hertz. It's a terrible racket. But as you walk around, you'll find places where it's really quite quiet, and other places where it's really loud. And the reason is because you're different distances from the turbines. And with a different distance, you're going to be at a different phase for the sound waves being produced by the turbine. And so there's some places where you can move to, and the waves are coming in and they're, like this, out of phase. Out of phase means you have destructive interference at that location, and it's pretty soft. You move 2 steps away, and they're in phase, and it sounds loud. And so that's beats in space, as opposed to beats in time if you have different frequencies. So beats in space is constant frequency, but different locations. Now, this is used in sound processing for your home theater. If you come to my house, I know my hearing's not the greatest anymore, but I still have it set up, for good sound. So I have the surround sound speakers and whatnot. Well, let's pretend that you only have 2 speakers, because that's the simplest one for us to model. If you have something like Ashley says, "Oh no!" You're watching the TV screen. The people who process the sound for the show want you to believe it's coming from Ashley. And so they will actually adjust the frequency, but the phase. That is the time when you reach the peak for the left speaker versus the right speaker. So you hear one just a little before the other, and it gives you a triangulation to say, oh, she's over there. If they want to be directly in front, they'll put them perfectly in phase. What if instead you're walking through the forest and they want to play this ominous sound, Okay, how would you go into the water with shark's face? They want this ominous sound that's coming from all around you. What they do then is they make the speakers out of phase. If they make them out of phase, then at the center you have destructive interference. And so it's kind of dim where you are, but you're going to hear the sound as if it's coming from all around you because you're in a place of a dead spot. And so you can get a different sense of where things are coming from by playing with the phase and this property. And now, does anybody have a sound bar? I don't, but anybody have a sound bar with their stereo system? Well, sound bars just have a whole bunch of speakers. And with a whole bunch of speakers, you can change the phase incrementally, and you can make it sound like sound is coming from any location in the room by having the phases different remember the phase is the time when you're at the maximum for the wave. And by shifting those, they can make it sound like the sound is coming from different locations. So the sound bar is a cheaper way of getting surround sound. In my house, I have what? It's, I think, 6 speakers plus the center and the woofer. And, I wanted it to be special. Now the last thing before we can do the lab. We did resonance on a string. Now, I talked about these tuning forks, and these pictures are for tuning forks because the tuning fork works the same as a tube. We have tubed instruments here. I have a number of them. Tubed instrument. It has a whistle here. This is called a whistle. When I blow air through here, I have air that goes underneath that whistle. If the air is moving, what does that do to the pressure?
It increases and decreases.
Okay. Decreases. The faster the wind's moving, the lower the pressure. So I'm going to have lower pressure inside. Well, if I have lower pressure inside, what's going to happen with the hole? Go ahead. Air is going to be pulled in. But that air pulling in causes a little turbulence, and that turbulence basically stops it. And so I have air pulled in, stop, pulled in, stop, pulled in, stop. And the rate at which it gets pulled in and stopped depends on how fast I'm blowing. And so I'm driving different frequencies by blowing at different speeds. Now I'm going to blow at different speeds, and you'll notice it's not just changing pitch. In fact, you won't notice change of pitch initially. What happens when I blow harder versus softer? First, the simple answer. What's the difference? Louder and softer. Okay, we're getting different amplitude because the air is rushing in faster or not as fast. But then if I blow harder, you probably heard it warble a little. So if I blow harder, what happened then?
Changing pitch.
It changed pitch. So I can change the pitch by blowing harder because when I blow harder, the rate at which it's doing that in-out thing goes up. It's only going to play the resonant frequency. I'm actually driving with lots of frequencies. It's only going to play the resonant frequency. I blow harder, the frequency range that I'm producing goes up, and it shifts to playing a higher harmonic. So it's going to play the fundamental, like this, and the first overtone or second harmonic, like that. And so there should be octaves. The difference between the first one and the second one. If I blow super hard, we'll just go deaf. I can't blow hard enough to get the next one. Kind of got it. I have another one. This is just the same thing, but it's longer. What difference will it make if it's longer? It's going to be lower. Why lower? Okay, we saw when we worked the wave on a string, we had a note at each end, right? Here, the pressure at the opening is atmospheric pressure. So this has pressure unchanging at both ends. It's a pressure note at both ends, just like a wave on a string was a displacement note. Now, with sound waves, we can talk about pressure or displacement. It's displacement antinodes when it's a pressure node. So it's displacement antinode at each end or a pressure node at each end. Let's go with pressure because that's easy to understand. Open to the air is going to be atmospheric pressure. So this is going to have the exact same boundary conditions as a wave on a string, hence the same resonance conditions. So the frequencies this is going to play is going to be n times v over 2l. So if I make it longer, I'm dividing by a bigger number. It's going to be a lower frequency. So let's test it. I can't even make it play the low one. The fundamental I can't make it do. Like, that's not the low one, that's higher. There's. But I think that's still actually the second harmonic. That longer should play a lower note. This one here is a very clean example. All you band types, who plays percussion? Okay, James. Do you have to play these in band? Yeah. My sister was a percussionist. She usually played the timpani, but yeah, sometimes she played this one here. And this is called a whistle. That's the technical name. So, right? Why is it changing pitch? I'm changing the length. Now, this is a different kind of tube. What's different about it? It's still open here, but the other end is closed. It has a plunger in here. So this we call a closed tube, a different kind of instrument. What's the pressure going to be here where it's open to the air?
Atmosphere.
Atmospheric pressure, right. So that's going to be a node if we set up a standing wave. On the inside, where we have the plunger, the air pressure can be anything. It's like a wall. The pressure can be anything on the wall until I break the wall. And so it turns out if the pressure can be anything, the motion of the particles is stopped, right? The particles have to stop at the wall. They can't go through the wall. So it's a displacement node at the plunger, and that makes it a pressure antinode. So this has a pressure antinode at one end and a pressure node at the other. That's like this, which means it's a quarter wavelength for the fundamental. I can still change the pitch by changing the length. Yes?
So when you blow into like a glass bottle and it makes those different noises with the different levels of water, is that considered a closed tube?
That's a closed tube, and that's pretty much exactly what we're doing for lab today.
And then another one, for like the wine glasses when you ring them through, is that the same concept also?
It is, but it's much more complicated because with the wine glass, what you have is a circle. You have a circle and you're making a wave travel on the circle. Now this circle is continuous, right? There is no end to a circle. You just keep going around. Yes? Okay. But if you're going to set up a standing wave on a circle, it's going to have to go through a phase relationship where it repeats when it does one cycle. And so the circumference is effectively the same idea as the length of your string, and the circumference has to be an integer multiple of 1/2 wavelength. 1/2 wavelength? No, of a wavelength. So it's kind of the same thing, but you're setting up a standing wave on a circular thing. Okay, so we already started. DJ, I believe, pointed out that for the tuning fork or for a closed tube, the shortest length you can have is length equals 1/4 wavelength. If I'm going to go from node to antinode, where's the next antinode in this picture? I'll just draw and you stop me when I get there. Okay, so there's the first antinode. That's a node, not an antinode. Okay. So here's my next one. Oh, I thought I changed the pin. So this would be a 1/2 wavelength here and another 1/4, so that's 3/4 wavelengths. So the fundamental is a 1/4 wavelength, but the first overtone that it plays has the length as 3/4 wavelengths. Doing the same work we did before. Whoops, I forgot to put over lambda there. So the frequency for the next one, the fundamental frequency was equal to V over 4L. And then the next one was 3V over 4L. I don't think we need to go any further to see a pattern. What's the next one going to be? 5. And so what we do is we call this F3. And we say F sub n is equal to n times V over 4L, where n is equal to only odd numbers. Before, I didn't write what the n's are, but the n's could be anything. Come on, show up. So here, for instance, I had it written down. N could be anything for a string or an open tube. Open tube is open on both ends. But for the closed tube, we have the frequency is n V over 4L, where n has to be an odd number. So we call it an odd function. a closed tube doesn't play octaves. You can't double the frequency with odd multiples. So that's kind of a problem. Now, anyone here play well, let's go with the best instrument. Anyone here play a euphonium or a baritone? Ryan does. Good man, Ryan. Okay, how about anyone play trombone, trumpet, tuba, brass instrument? You do? What did you play? French. Oh my goodness. I am not going to ask you the question because French horns are crazy.
Yep.
Playing a French horn takes way more skill than I will ever have. Right, the best instrument is the easiest one to play, just for the record.
It was difficult.
Yes. Okay, so somebody else play brass instrument besides the French horn? It's hard.
Have you heard of the steel drum?
Uh-huh.
And I think that's interesting when you hit it, when it's like tapped in deeper with a bigger bass of a skirt.
The
Drum.
steel drums, they actually have different places you can hit and get different pitches by varying. It's really complicated, nothing I can explain. What I want to get to here is my baritone will play an octave. I can play a B flat, and with exactly the same fingering, if I blow harder, I can play an octave above that. But it's a closed tube. Where my lips are is going to be a pressure antinote. Where it's open, it's going to be a pressure note. How in the world is it possible for a closed tube to play octaves? I just told you it plays odd multiples. You can't get an octave with odd multiples. Any clues? It's acceptable to have no clues. Okay, I went over this with Ashley yesterday, so let's see if you remember from yesterday, just so I can have a student answer.
Sorry, I missed the question.
Okay, how is it that my baritone can play octaves when it's a closed tube?
So all I remember really was discussing like the end effect.
She's right.
Taking that into account as far as the length. I don't remember the rest.
It's conical in shape. First of all, I should point out that what we've been talking about applies specifically for cylindrical instruments. Conical instruments are going to be a little different. And with the bell on the instrument, for different pitches, it behaves like it's a different length instrument because the actual position where you have the pressure node is not going to be right at the end of the tube. It's going to be a little bit further out. And so we call that the end effect. And the end effect will be and with the diameter. So you have an effective different length of the tube when you're playing a low note than a high note. That's how you can play an octave on the instrument. Now, because Emily plays the hardest instrument that I know of, the French horn is designed so its fundamental frequency is like super low. Right? It's a really long instrument. And because it's got a really low fundamental frequency, you can play a whole lot of notes without changing your valves at all. I am told in some ranges you can play an entire scale just using your armature to adjust the notes, which I don't know how you do it.
Yeah, and then it's very sensitive with the bell part.
Yeah.
Just having your hand cupped a certain way changes what it sounds like. It could be in tune or out of tune, like by like slightly.
So the French horn is so squirrely, so hard to play because it has you're in the region where the overtones are very close to each other. Okay, so we've talked about the closed tube now. Here's a picture just showing the different geometries for making a note in a closed tube and the frequencies. And you see here, this is from our textbook. It called it F2 using 3 and F3 using 5. That's not standard. Standard is to just use F1, 3, 5 and not use the even numbers. It's easier to remember. So let's take like a short break because you've been sitting for an hour. I know I've been moving all over the place and I'm good to go. But go ahead and take a short break just so you can get some air. And we'll meet again just at 3.
it's. I think